Okay, 415, lecture number 2. And what happens today is that we will continue where we left from last week. And last week we started that subject matter of multi-body system dynamics. We started that by describing a rigid body, so a rigid body. And today we're going to continue from that, like I just mentioned. So the rigid bodies, that was the last week. Today we're going to look how is that we can describe a velocity and acceleration of a particle. And then something that is very important, with the utmost importance with you, is a concept called generalized coordinates. And then something that is, if possible, even more important than the concept of generalized coordinates, and that's the constraint equations. Uh, then the constraint equation is something that is playing a fundamental role in a multi-body system dynamics. Remember the last time we discussed that multi-body system is a system which experience or can experience large rotation. And the large rotation itself is not really necessary making a system to be a multi-body system, but the fact that the bodies are connected together via joints, that makes a multi-body system. And now how is it you can describe these joints, these mechanical joints? Well, you can describe those by using constraint equations. So mathematically, you express these joints by using constraint equations. And these constraint equations limits the motion possibilities within the single body. And how it limits, well, that's heavily case dependent. And we're going to learn a little bit of details on that subject matter later today. It's probably somewhere in the second part of the lecture today. But anyway, so these are the stuff that I wanted to discuss with you today. So let's get started by first looking at the few practical matters. Weekly homework. I got a couple emails wondering like what is a proper way to do the weekly homework. And you can do it whatever way you want, but there is a strong recommendation to use a symbolic math tool, whichever you prefer. And it can be MathCAD, it can be MATLAB based. That doesn't really matter which one you wanted to use. But it is highly recommended that please start using the symbolic math tool. And it's not just that it helps you to do this weekly homework, but it's a great tools and then great asset to you when you are going to written exam or these midterm exams. Because in midterm exams, we do have some computational tasks. And once you have everything pre-made or ready-made in a symbolic math tool, it definitely helps you to answer those questions and make sure that you're not getting confused too easily. So highly recommended to use a symbolic math tool. If you insist, sure, you can use a handwriting or whatever computation you want. And it's okay if you want to use a handwriting. Then the only thing that is important is that the PDF submission is the one we accept. So don't send a letter to us or don't send an email, but the PDF submission through the Moodle database, So that's critical. We don't accept emails. So how to do that then? Well, this is a screenshot from the Moodle database. So you do it in a way that you're selecting, first of all, this first period, which is the one that we're experiencing at the moment. And then the first assignment was provided to you in a task number 1. Submission is always in a following task. So now if you got the first assignment in the task number 1, submission tool will be available in the task number 2. And the deadline, like mentioned earlier, the deadline for the first weekly assignment is this week Sunday, which is the 19th of September. What time? That's going to be at midnight. Actually, it's not going to be midnight, but I think it is a 5 minutes prior to midnight. So it's at 23:55. And that's when the system automatically is closed. And it's seriously closed. So then you cannot submit it after that. So this, you are simply too late to do the submission. So please keep that in your mind. And you got an email from Suraj regarding tutorials, guided tutorials. So please take a look at his email. and he contacted you via Moodle. So if you don't have that in your screen at the moment, go ahead and log yourself to Moodle and take a look what he explained about the guided tutorials. One more practical thing is that I decided to offer you one more opportunity to upgrade your final grading. And final thing to do so is that we actually set it up a website a while ago, which is called edutemeco.com. And there's a material, there's a course. If you look at this one here is a very small font, but it says simulation of a mechatronic machine. And you can do this course by looking at the videos, which are 5 minutes in length, sometimes even shorter than that. And then there are short questions regarding the topic and the content of the lectures. By answering those questions, you can earn extra 25 points. Now, I don't have the equation with me, which shows how is that the final grade is computed. But remember that there was two mandatory items. This written work, written examination, and then simulation assignment, and then some additional tasks that you may or may not do. And if you decided to do those things, you can upgrade your final gradings. That's the whole point. And these additional tasks are weekly homework, in-class quizzes, and now this Edu Temeco website. So you can get a total of 0.75 points. So take this opportunity. And actually it makes sense to check it out, this Temeco site, because it definitely helps you to prepare yourself to written exam. And it gives you a kind of little bit of different kind of perspective, the whole subject matter that I'm able to deliver in these lectures. And those are with the high quality. I can guarantee you that. Not made by me, but some other fellows, and they really are capable to do some good high quality lectures, videos. Okay, multi-body system dynamics. So let's summarize what we discussed a week ago. So multi-body system can be used to analyze a wide variety of applications. So it can be applied to robotics, like shown here, for different kind of mechanisms, and mobile machines and vehicles and many other things, biomechanics included. So it's a very broad method, or the method can be applied to broad applications, a wide variety of applications. The only thing that actually is important is that it's powerful method if you apply that to system that is a multi-body system. And like I just explained a couple of minutes back, multi-body system is a system that consists of one or more bodies that are connected together or ground by joints, constraint equations. Today we're going to take a look closely about what these constraint equations and joints, what is their concept, and what kind of advantages they can offer to you. So that's pretty much the topic of today's lecture. We also look a little bit about how is that we can describe multi-body system mathematically. And something that is extremely important to understand, that we are assuming that the body is consisting of infinite number of particles. Then what is a particle then? Particle is something that is not the real thing. It's like a mathematical quantity, something that you cannot see in real life, but is helping us to define bodies. So the particle is tiny dot, if you want to have any physical interpretation, what the particle is about. So it's a very tiny dot. And because it's so tiny, it don't have a rotational degrees of freedom. No rotational degrees of freedom. In this class, very often I'm offering an opportunity you to answer in-class quizzes, and one of the options is typically rotation of a particle. Rotation of the particle is like Santa Claus, not existing. Well, if you did not know that the Santa Claus did not exist, here's another piece of information to you. So it's not existing. Rotation of the particle, it's just not available. Why? Because it's so small, so small. So what that means for us? So it means for us that the only thing we need to know about the particle is where it is located at. That's the whole thing. So we don't need to worry about its rotation because, again, non-existing thing. So What's the way to describe this particle with respect to reference coordinate system, which typically is the one that is called global coordinate system? Well, the easiest way to make it happen, well, just, long story short, is that we should employ a body coordinate system, body reference coordinate system. And the body reference coordinate system is something that is attached to body, and it travels and rotates with the body. So you cannot separate those two things, body reference coordinate system and a body. This gives us a great advance. And the great thing that comes along with the body reference coordinate system is that within this coordinate system, we can easily describe every single particle that belongs to the body by using vector u-bar. So let's take a look at the concept of vector u-bar in a second, but it's a vector that is constant in the body reference coordinate system. Okay, so now things becomes a bit easier, because what we need to do to describe this guy here, the particle, with respect to this global coordinate system, we need first of all to describe how much there is a translation of the body coordinate system. All right, that will be described by vector r. Vector r in a planar case consists of two components that are rx and ry. Those are projection in a global x and y axis. All right. So then let's write this equation here. Then we need to take the orientation of body reference coordinate system into account. That we can take into account by using a 2x2 rotation matrix that maps description from body reference coordinate system to global coordinate system. And I see that I have an issue in my camera. Let me see what is a problem here. Come on, so why? Why? Here's my camera cable here. How come? How come it is not cooperating with me at all today? Okay, let me connect that in a little bit another way. Just a second. Okay, so how is it? This is okay. And I'm back. Sorry about that. Yeah, so I was about to explain this guy here, this 2x2 rotation matrix, which maps representation from body coordinate system to global coordinate system. So what this means for us, so we can actually convert this vector u bar, which is initially expressed by using this coordinate system, to be expressed by using this global coordinate system. Let me change the color to make this a bit more clear to you. So we are moving, or we mapping this guy from this coordinate system to this coordinate system. And that's going to happen with help of this 2x2 rotation matrix. And that's the way we can describe particle with respect to global coordinate system. Now this guy here, this 2x2 rotation matrix, is representation of body coordinate axis. Coordinate axes are having the 90 degrees angle with respect to each other. So not looking too good. But it seems that I'm back. At least it says that my stream is healthy again. I'm thinking that the problem is somehow related to my camera. I don't know, but I'm thinking that is somehow the one that is causing all these problems. And camera, is the one that is stocked. That's okay. So let them be stocked. What's the deal with this vector U bar? Yeah, not looking too good. I know that is not, nice, but you kind of make me looking pretty. That's just impossible. So let's just use the still picture, and I'm gonna try to do something to my camera during the break. Don't know why it is behaving this way. That's a big mystery to me. So let me make the final setting here to try to convince it to cooperate with me. And then somebody's asking about the student ID number, so please, can you please help? The way you can find the student ID number is that you can go and log yourself to sisu.lut.fi. All right, so vector U bar. So vector U bar is a kind of special person because, as mentioned earlier, it is a constant vector, meaning that if you're looking at the one particular particle, it's always constant. So the particle cannot move with respect to body reference coordinate system. But at the same time, vector U bar is the one that is scanning every single particle within the boundaries of the body. So meaning that the vector U bar reaches all the way here and every other position between these two extremes. So it's scanning every single location. But once it finds the one a single particle, it's constant representation. Now the body reference coordinate system can be located anywhere you want. The vector U bar or nature of the vector U bar depends a little bit on that. Because of course, once the body reference coordinate system is located in the middle of the body, then the U bar scan is different versus when the body reference coordinate system is located in the one corner of box-like body, like shown in this example. So that's for your information. And also keep in mind that the body reference coordinate system can be located outside of the boundaries of the body. This is, by the way, a typical question you can see in written exams as well. Okay, so let me move on. One more word about this rotation matrix. So this is the way we're describing a particle with respect to global coordinate system. And I'm committed to repeat this equation to you more than 1,000,000 times. So you will be absolutely bored to see this equation over and over again. And why is that? Because this is essentially our means to describe the kinematics. But this is it. Rest is actually very mechanical in a multi-body system dynamics. So this is the only equation that you need to know. Rest you can derive. And so how it goes then? So you can find the velocity by differentiating this once with respect to time. You can get an acceleration by differentiating this equation twice with respect to time, and so on and so forth. So it's very essential. It helps us to describe these constraints, these joints as well. So we're going to practice the equation a lot. One more thing. I mentioned earlier that this rotation matrix is orthogonal in a sense. So these vectors that are forming from the column of the 2x2 rotation matrix are unit in length, and they are perpendicular with respect to each other. So that's the definition of orthogonality. Orthogonality is a nice mathematical feature because matrix inverse can be found in simply by taking a matrix transpose. What that means, it changed the mapping order. So meaning that it was not just frozen, but I was also offline, which is a big surprise because here in the university, everything should be as strong as possible. I don't get it. I don't get it. So let's just hope that things getting better later today. But my first in-class quiz to you is that what is the role of rotation matrix? First option, it describes the rotation of a particle. Hear me. It describes the rotation of a particle. Remember what I just explained about the rotation and the particle? And then it maps the body reference coordinate system and the global coordinate system. Option number B. Option C is maps body translation and rotation. And then the final option describes the translation of body A. Let me put the Socrative on so you can answer this question. So go ahead. I see. Oh, by the way, something that is good to see that I can see that there are more students than it was just in the beginning of the lecture. So now it seems that we have 53 students. It was actually even higher than that a couple of minutes back, maybe because of these technical issues you guys got fed up. Don't know. Okay, I got 7 answers already. 60 students in my soccer team, so it's looking promising. It's looking very promising. Okay, and while you guys are thinking this, I'm gonna move on, and I will get back to this in-class quiz in a second. Not in a second, but after a couple of minutes. Now I just need to find it out, like where is my pointer is traveling. Here, there it is. Okay, something that is a bit interesting, and I would like you to be aware of that. Just like a short overview, is that how is the kinematics in three-dimensional space? Well, as you probably already guessed, it's exactly same than kinematics in two-dimensional space. Another technical issue that I seems to have that my slides are a bit moved, but that's okay. Let them be like that. So in a three-dimensional space, in spatial cases, we have actually coordinate axis or coordinate system that consists of three axes, which is X, Y, and Z. This is the one you can see in a real life, anywhere you want in a real life. So in that case, vector R that describes the translation of body reference coordinate system is a vector that consists of 3 units because it has to have a projection along the X, Y, and Z coordinate axis. Rotation matrix is going to be 3 by 3 rotation matrix, which we're going to take a look how is that you can do that in a minute. And the vector U bar, that's the one that again consists of 3 components because body coordinate system has a 3 axis. So that's where they're coming from. The only difficult thing is this guy. There's a description of rotations. And it's a mathematically a little bit involving. And it's a mathematically a little bit involving because even though that the body can rotate in 3 different ways, its description in mathematics is a bit cumbersome. And it's due to the fact that whatever you're using 3 rotational parameters to describe the body orientation, they are suffering from something that is called mathematical singularity. And the mathematical singularity is that rotation may not be clear, so you may not be differentiate what rotation is what, or there may be certain components in rotation matrix that you're unable to compute because of the singularity. So that's a little bit of problem. Anyways, one of the most commonly used description of rotation is a method based Euler angles. And Euler angles is, well, it can be used in a many different sequence of rotations, but most often used sequence of rotation is the one that is shown here. So it's Z, X, Z sequence of rotation. And where that is coming from? Well, I have no other clear explanation than gyroscope. If you look at the gyroscope, depending on how you put the gyroscope, but this clearly is something that you can see the rotation sequence to be Z, X, Z. And using these 3 sequences, you can put your body any orientation in space you want. So it's not limited at all. So how these Euler angles goes when using the sequence of Z, X, Z rotations? Well, it goes in such the way that you are putting 2 coordinate systems to be parallel in the beginning. And then you will take a hold of the one coordinate system and you're rotating the coordinate system along the Z coordinate axis, like is shown here. There's a rotation along the Z coordinate axis. Amount of rotation is this guy, which I'm not sure how to pronounce, but I think it is psi or phi. Doesn't really matter. I think it is psi. All right. So then you have system where the coordinate system is rotated around the Z coordinate axis, amount of psi or phi. But don't get confused about my pronunciation. You just take a look at that. This is how much it is rotated. All right, something very important comes next. You take a hold of once rotated coordinate system. let me repeat, one's rotated coordinate system. And this time, you will take a hold on the coordinate axis x, and you will introduce the amount of rotation that is amount of theta here. All right. Then you take a look of 2 times rotated coordinate system, and you take a hold of that 2 times rotated coordinate system, this time in the axis z again. And you do your final rotation, which is this amount, c, and that's it. Those are your 3 successive rotations. And you can mathematically describe each of these components. And once you do that, then you can get this rotation matrix in 3-dimensional space. How to remember the direction? Oh, okay, let's take a look at the direction. So let's take a look at that in a minute. But again, the idea is this: you do 3 successive rotations, and the positive directions. These are the ones that you can. First of all, depends on how is that you can describe your coordinate system. Is it going to be a left-hand coordinate system or right-hand coordinate system? And in a left-hand coordinate system, the good rule of thumb is that you use your left hand, like this is my left hand, to put your coordinate system, and then you're using your right hand, and you put your thumb to same axis that the coordinate axis you want to rotate. These fingers telling you what's the positive direction. That's how it goes. In this coordinate system, then it's going to be another way around. So it's like this is how it works. And this, by the way, is something very important for us because, this coordinate, this left-hand coordinate system, right-hand coordinate system is something that is very important in a spatial multibody system dynamics. And I'm proposing you that, this class here, this simulation of mechatronic machine, let's make an own group for that, like own gang. And gangs, they always have their signs, like how to say hello, like East Coast, West Coast, this kind of thing. We're not going to do that, but we do this. Left hand, you can do like this and say respect. This hand, right hand, and this was a left hand, respect. Right hand, multibody. Pick the one you like the most. You can use both hands, respect, multibody. And the next time that I see you in Prisma or, I don't know, somewhere in the university, don't say hello, but say respect or multibody. Respect, multibody, even better. Okay, back to the real deal. So where I am now. Was there any other comments? Okay, in class quiz, somebody was asking like, what is going on with the in class quiz? So let me show. Here it is. Okay, game is on. Success rate competition. What is the success rate? Make your guess. My guess is this. 65. 65. 65 because this is no longer easy thing. You need to really pay attention to me to be able to answer this correctly. And while you're doing that, let me adjust my screen because for some reason my need to do this. Put it back where it was. Oh, yeah, like this. Oh, there's 100%. Well, 100%, it would be nice to have 100%, but I don't believe that by myself. Why? Because of this option number 1. Option number 1 always makes people confused. I really don't know why, but it seems to make people very, very confused. Okay. And here it goes. Results. Okay. Remember what I said. I say 65. 65. And I was the winner. So I was the one that, I'm a winner of the whole game. Let me see if there's any other winners. No, it was just me. Isn't that really the case? It looked that it was only me. Yeah. Let me scroll down here. There is a 68. 68 is a little 67. 67. 67. So let me announce the winner. Ah, there's a 66. 66. That's not close enough. So winner is me. Okay. Description of particle, absolutely incorrect. Very incorrect. Why? Because rotation of particle, non-existing. There is a rotation of body reference coordinate system, but not rotation of particle. This option will be available in my future in-class quizzes, very often. Never ever pick that. Never ever pick that because this is so incorrect that you don't believe it. So don't use that. So still somebody is saying that you cannot see my frozen P. Okay, anyways. Then maps the body reference coordinate system and global coordinate system. That's exactly what the rotation matrix is doing for you. Maps the translation and rotation. No, those two things are not mapped because capital R describing the translation, rotation matrix describe the rotations. Describe the translation of body A. No, that's not the case. That's vector R that's doing that job. Okay, so let me take it off. No, this one. And let me go back to my PowerPoint presentation. Okay, so how it goes in mathematics behind these Euler angles? Well, like I said, you can describe these individual rotations by using 3x3 rotation matrix. It's fairly straightforward. And let's just take a look at that shortly, like what it is straightforward. First of all, remember the first rotation takes place around z-axis. That can be easily seen here because, here is where the rotation takes place. Then you can see that there's like 2x2 rotation matrix, which is exactly the one we've been looking at previously as a submatrix. So this is the one that describes the first rotation. Second rotation takes place around x-axis. This is it. Tells you immediately that the rotation takes place around x-axis. This is your 2x2 rotation matrix. So what is left outside of that columns and rows that is reserved to this guy is going to be your 2x2 rotation matrix. Final rotation will be around the z-axis. And again, here is your 2x2 rotation matrix. And once you do the math, once you multiply these matrices together, this is how you can deal with the successive rotations. Then you can get finally this description of rotation matrix, which I'm not expecting you to memorize. But I would like you to be aware of the concept where these Euler angles are coming from. So they're coming from the 3 successive rotations. Most often used sequence of rotations is the one that we just look. This one. So is your camera mirrored? Yeah, but I don't know. I think that it is. I think that it is mirrored. Sorry about that. Yeah, I think that it is mirrored. Next in-class quiz is this. In Euler angles, an often used sequence of rotation, one we just look at is x, y, z, z, y, x, z, y, z, z, x, z. And you're good to go. So tell me, which one we just looked at? Which was the sequence we just studied? 4 options, 1 only is correct. Think about what is a sequence of rotation in a gyroscope. That could help you to answer this. And again, it doesn't really matter that you can use another sequence as well, but this is the most often used, very often used sequence. What do you think of that? Let me just shortly tell you a little bit more about 3-dimensional. This is a mathematical properties of rotation matrix. This is something that I already explained to you. So the transpose and inverse is same thing. And that's because the rotation matrix is orthogonal. That's the reason behind. And if that's the case, then transpose of the matrix multiplied by matrix itself will give you identity matrix. An identity matrix is going to be a matrix which is a 0 except the diagonal components are ones. So this is a 2 by 2 diagonal matrix. This is a 3, excuse me, this is 3 by 3, excuse me, this is 2 by 2 identity matrix. This is 3 by 3 identity matrix. And in three-dimensional space, the order of rotation cannot be changed. This is something that you cannot play with. And the game is on. So, as soon as you enter your answer regarding the Euler angles, you could enter your guess about the success rate. My success rate is, my guess regarding the success rate is this. 55. Why? Because really to answer this correctly, you need to pay attention all the time to me. That's a challenge. I have to admit that's a great challenge. Okay, let's. I have so much material today that I would like to cover that I'm gonna move on a little bit. Next subject matter is something that is very brief, very mechanical. So what we're going to do is that I'm going to introduce you velocity and acceleration of a particle. This was mentioned earlier. That is very simple. You just take the description of particle, you differentiate that once with respect to time, you will get the velocity. You differentiate velocity one more time with respect to time, and you have an acceleration. That's it. So that's why this equation that you should memorize already this time is pretty much the only thing you need to know. This is like the rule we decided in the very beginning. This is how we're going to describe bodies and particles, to be more specific. And I have 71 answers. So how come I have that many answers? It looked that I have 66 views in my YouTube streaming, but that's good. Good that we have that many answers in in-class quiz, and the success rate is this. 63. 63 is actually, well, roughly what it was, but I was wrong this time. I thought that we're going to score lower than that. Let me see. Do we have winners? Oh, there's one guess that is 3%. That's very low percentage. Very low. 63. Seems to be a tough game today. You guys are just simply guessing too high numbers. 61. So we got the winner. 61. Good job. Where's my pen? There. Okay, let's move on. Velocity and acceleration. Okay, here. So how it goes? Like I said, it's simple. Sorry that I'm blocking your view a little bit, but that's okay. Oh, what the heck? It seems that again, my screen is moved a bit. I don't understand why. So let me adjust that back. Here and here. Okay, so velocity of a particle. That's simple. So you just take this equation that you already know very well. You differentiate that with respect to time. That's all you need to do. So here's your operation. So it's a partial this description of particle with respect to time. So the first thing we do is that we differentiate the vector r with respect to time. And what we're going to get as a result of that, we will get the translational velocity, denoted as r dot. Okay? Then the component that is left is this one here. So it's a partial rotation matrix multiplied by vector u bar, differentiated with respect to time. Well, this guy consists of two components, so you have to differentiate it like first with respect to rotation matrix and then with respect to vector u bar. Remember, vector u bar is constant, so it's not changing as a function of time. That's why this component can be deleted. So it's not affecting the velocity. What is left is this partial operation of rotation matrix with respect to time. So this is what we need to take a look in details to have a good understanding what it is. Okay, so rotation matrix dot is equal to the partial operation of rotation matrix with respect to time. And now we need to use a little bit of mathematical skills, and we need to use a chain rule of differentiation because time is involved in this guy here, this rotation angle theta, but not explicitly here in this equation. So that's why we need to use this chain rule of differentiation, this one here. And once we use a chain rule of differentiation, we're differentiating this trigonometric function and then something that is inside of the trigonometric function, and that's this angle theta. So when we differentiate the angle theta with respect to time, we will get theta dot, theta dot. The same holds for every single component of this rotation matrix, same procedure over and over again. This dot here, this is equal to an angular velocity with respect to global coordinate system. That's what it is. So angular velocity, and you can express this mathematical operation a little bit more in a delicate way, like shown here. So the rotation matrix, or differentiating, when you're differentiating rotation matrix with respect to time, you can express it in such a way that is angular velocity multiplied by something that is called rotation matrix subs index theta. A theta if you want, if you may. Okay, what is this guy here? This is a rotation matrix which is rotated 90 degrees in anti-clockwise direction. So if you have a rotation matrix, let's say body reference coordinate system like this is X, this is Y. So this guy here, which is again called like this, will be the one that is rotated 90 degrees with respect to your original body reference coordinate system. So this is going to be your new x-axis. This is going to be your y-axis. 90 degrees angle difference. And you can see that clearly when you look at these components. Again, we are having orthogonal matrix, but rotated ones. So finally, when I do the math, how it eventually look like, here's my description of velocity, which consists of two components. Translational velocity, which is very simple to understand. You know, if you have here body reference coordinate system and potato-shaped body which is running this direction, it is telling that translational velocity. All right. Then I have second component that is related to rotation. So this one here is angular velocity, and this one here is the one that is maps the matrix to be 90 degrees angle with respect to original body reference coordinate system. That's the whole thing. And again, what is this is describing to you? This is describing how is a particle, one single particle described by vector u bar with respect to global coordinate system. So again, it's a particle. How you know that? Because, you know, if you look at what is a final outcome of this is a vector r dot, which shows the velocity of this particle. Excuse me, let me write it this a bit more clear way. With respect to global coordinate axis. So these obviously consist of two components, r dot x, r dot y. R dot y, I'm sorry that I'm messing. So let me write this a bit clear way. R dot x, r dot y. That's how it goes. And now I'm blocking the view. Okay, getting better. All right, so that's about the velocity. One more step to take. So can you guys handle that, or would you like to have a break? So let me hear your comments. Sorry that I'm blocking that view so heavily. So let me write this one more time. Last time. Here it is. And these are the dots, of course. One more step. Yep, one more step. I hear your can-do attitude. Very nice. Happy to hear that. So I'm with you. So let's make it happen. So one more step, and then we can, if we still find our way back to the toilet, then we can have some break. One more step, which is actually very mechanical, very simple thing. So now this time I'm not going to look at the details that heavily anymore. We're just going to rely on the fact that we all know the mathematics. And if not, we can always refer to this Khan's Academy if you want to know that, if you really insist to know the details, which I'm even not recommending you to do because big picture is way more important than the details here. So if you get lost with the details, your life will be difficult. Okay. So here was our description of velocity. Now let's differentiate that one more time with respect to time, and we're going to get an acceleration. So it's going to be very simple. The first component is a single component, a symbol. So let's just differentiate that with respect to time. We will get the translational acceleration. Okay. Then what we need to do is that we need to take this component, because obviously there are two things, theta dot and is a theta, that both depends on time. So we need to use again, our mathematical skills to handle that component. So let's first differentiate this guy here, which is in the middle. So it's going to be, of course, this angular velocity, and then there's a rotation matrix that is differentiated with respect to angle theta, dot. Look at, there's a dot here. And then the vector u bar, which is business as usual. No surprises here. And then we're going to differentiate this angular velocity. This is going to give us angular acceleration. Rest will be with no changes. Okay? Then I'm going to give you something, which if you don't trust me, you can go ahead and verify this from the lecture note. I'm going to tell you that, okay, using the same concept we did two slides back, you can write this component, which is a rotation matrix, first differentiated with respect to angle theta, and then there's a dot. When you do this mathematics, you can get this equation, which is a minus angular velocity multiplied by original rotation matrix. Now, when using all this material, when putting this, this material, substituting this one here to here, sorry, that is a little bit messy. This is what you can get as a result. Now, here comes something very important. You see that our acceleration consists of three components. Translational acceleration. There's something that is quadratically related to velocities. That's the middle one. And then the one that is related to angular acceleration. That tells you that inertia force is too, whatever we will end up to have to discuss, or whenever we have a time to discuss about inertial forces, they will be also related to linearly to acceleration and quadratically to velocities. And I'm sure what you're hearing right now is like unclear connection, which is okay. Don't worry about that. We will take a look at that after, I don't know, 4 weeks or something. So no worries. Okay, so that's about it. So let's look at these components. These components have a clear physical interpretation. The first one is obvious. That's a translational acceleration component. Then there's a normal acceleration component due to the rotation. Let's take a look at the interpretation in a minute. But this time, good you to know that is a normal acceleration component due to the rotation, and tangential acceleration due to the rotation. Sometimes somebody asks, like, okay, what about the Coriolis acceleration? Where's the Coriolis acceleration? Well, depends what you mean about Coriolis acceleration. So, in this kind of mechanical simulation we usually conducting, we don't take the Coriolis acceleration due to the rotation of Earth into account. Yeah, it is a, kind of simplification, because if I move from here where I'm sitting at the moment to my office door, in theory I'm experiencing Coriolis acceleration. And that's because, by the definition, Coriolis acceleration takes place when there is a particle moving in a rotating disk. So where is a rotating disk? Earth. When Earth is moving around, that's a rotating disk. But when I'm moving here to my office door, I cannot sense that Coriolis acceleration. Somebody say that you drink enough alcohol, then you can sense the Coriolis acceleration. Yeah, maybe that's the case, but I still doubt. I think the reason that you're unable to keep your balance is not because of the Coriolis acceleration, but something else. But anyways, that's by the definition. That's what the Coriolis acceleration is about. Okay, what about us? So, we have let's say this circular shaped body. How is a particle capable to translate in this kind of body? Cannot translate, because vector u bar, remember, is constant. That's the reason. So, oh yeah, there's a comment about Earth is a disk. Yeah, Earth is a disk. That's right. So Coriolis acceleration is something we don't take into account, because the way we have the kinematics is all about how you're defining the kinematics. And the way we do it, we don't have it. We don't have it. Somebody else can use a different way, and then it may be there, but we don't. Take a look at these YouTube videos that are really outstanding explanation about what is a Coriolis acceleration. It really depends on your viewpoint, how you how is that you're putting yourself in a position with respect to motion. Okay, and the flat Earth confirmed. Yeah, that's right. That thing too. Okay, and then the physical interpretation that I promised to you. Here it is. Here is a physical interpretation. So this is a particle. Oh my God, I did something really weird. I jumped to, I don't know how this is possible. How come? I think I somehow touched this screen. Okay, so let me put it like this. So here's a particle. This tangential acceleration is pointing this direction, because look at this. Is this 90 degrees angle, and then with respect to rotation, and then this is the one that is pointing this direction, and that's how it goes. So these are the three components. Let's look at those bit later when we are looking at the different kind of inertial forces. But this time, let's leave them a little bit aside. Now let's discuss something that is, and now this jump back to this original location. Let me modify it. Here. Something that is very, very important. Oh, there it is. Oh, it's back. So, yeah, so this is maybe this would be a time to have a break, but I'm not going to have a break today. And the reason being that I've been wasting time because of these technical difficulties, so I'm simply going to go. Okay, so let me see how healthy is my stream. So it looked that is okay. Okay, two things that are very, very important. Generalized coordinates and constraint equations. And let me get started by generalized coordinates. And again, everything goes back down to this equation that we learned in the very beginning, this equation here. Now, what we need to do next is that we need to be able to identify variables that are describing the body configuration. Body configuration. The body can translate and body can rotate. Which are the variables that are telling us how is a body translation and orientation? Now this is hidden, or this information is hidden to this equation that we already learned a while ago. We just need to look at the different components and we need to identify whether or not the components can change the numerical values because of the translation or rotation. And once we're able to detect those values or components that are capable to change their numerical values, those are the ones that are called as generalized coordinates. And what follows after that is that these generalized coordinates are something that are kind of like our target from that on. We need to solve these generalized coordinates because those are the ones that are telling us how is a body configuration. That's the whole thing about the dynamics and kinematics. So we need to know where the body is located. And who is telling that information for us? That's generalized coordinates. Okay, let's take a look at this whole thing about by first checking out this potato-shaped body. Potato-shaped body. And then in a potato-shaped body, there's a particle P here. Particle P. And the particle P with respect to global coordinate system can be expressed by using this equation that we know already back and forth. All right, then let's just walk together and let's look at each one of these three components to identify the components that can change their numerical values. First one is this one, R, which describes the translation of the body reference coordinate system. Okay, can it change its numerical values because of the rotation or translation of the body? Yes, it can. If the body translates along the global coordinate axis, X, its numerical values will change. And the same happens when it moves along the global Y coordinate axis. So obviously, this vector here is something that is generalized coordinates. Okay, so then comes rotation matrix as a next. Rotation matrix, we have cosine theta, sine theta components. So obviously the theta is the one that is possible suspect. How is a theta? Can it change its numerical value because of the motion? Yes, it can. Because of the translation, the theta can change its numerical value. So obviously that is our generalized coordinates. What about vector u bar? No, vector u bar cannot change any numerical values. Why not? Because remember the vector u bar indicates that it is described with respect to body reference coordinate system, and the particle cannot move with respect to body coordinate system. So not the variable. So let's make a list of variables. So to be capable to describe the body configuration, we need to know Rx, which is a component of this guy, Ry, which is a component of this guy, and angle theta, which is a component of rotation matrix. This is our vector of generalized coordinates for this system. So if we're going to have another potato-shaped body, we need two more coordinates. Excuse me, three more coordinates. So it's going to be a total of 6 generalized coordinates. 3 coordinates to the body number 1, 3 coordinates to body number 2. So that's how it goes. So let's take a look. So let me move on in my explanation as soon as I'm able to find my pointer. Here it is. Okay, in 3-dimensional space, we have either 6 or 7 components per body, depending the way we're describing this orientation. So if we're using Euler angles, we're going to have 6, because 3 translations, 3 rotations, so that's a total of 6. But we could use a method which is using 4 parameters to describe the body orientation. So 4 parameters plus 1 constraint, that's possibility, which we haven't discussed in details. And in that case, you will have 7 coordinates. Don't worry about too much about the spatial case, so it's not that important. But let me ask you this. So if you have one body A, what are the generalized coordinates? If you have this body, what are the generalized coordinates? And the options are Rx, Ry theta, U bar 1, U bar X, U bar Y, Rx, Ry theta, U bar X, U bar Y, and theta. Only one is correct. But which one is correct? So let me see. Let me put it on. So the game is on again. This time, how is the success rate? This is not easy. I mean that you may think, okay, this is so easy that is ridiculous. You need to do some thinking, and you need to remember what I just explained to you. What I just explained to you, that's the key to success. But what's the success rate? So the game is on. Would you like to learn my, we got started by 31. 31. That's definitely a low number. My guess, now you guys are shooting really low. 45 that's next. My personal guess is this. Oh, I missed. My personal guess is this. 85. 85. Now we got very, very low numbers this time. So the numbers, the maximum, I think it is 73. I'm the only one that is voting that high number. Others, you are voting very, very low number, 72. But come on, guys. I just explained this whole concept to you. And I said a number of times that this is very, 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 I think that I used 3 times very important. So we'll see. Okay, are we ready? We have 65, excuse me, yeah, 58, excuse me, 58 students. I was mixing my screens. So soon we're gonna have a 60 answers and then, 61 answers. So then I'm gonna close the game. So you ready? And the success rate today is 62. Oh, the number is still increasing. Okay, now I think it is stopped. 71. 71 is very nice. So let me see. I was, again, by myself. I was very close to hit the spot. There is a street name or artistic name that win this game. I don't know who is this guy. Okay. And then somebody else. Yep, you're right, Joe. You got that too. So you got it right. You got it right. So let's move on. Let me hide this one. And let's look at the next important thing. Computers are running really slow today. Okay, constraints. Concept of constraints. And again, the window is moved a little bit, but let me see if it is. Yeah, it's not coming back, so we fix that final time today. So here's my pointer. Let's put it back where it's supposed to be. Okay, constraints. So what's the concept of constraints? Well, I said earlier that the constraints are the ones that are representing the joints. And what the joints are doing for us? Well, they are limiting the motion possibilities. Think about the connection rod as an example. Connection rod, this guy here, if it would be a free body, it could have 3 degrees of freedom. It can translate 2 different ways and rotate in a 1 different way. Well, 1 way, not in a different way. And now because it is a part of the mechanism shown here, so its motion is no longer free, but it has to follow the motion of its neighboring bodies. And that's because of the constraints. That's because of the joints. So joints are forcing the connection rod to move in a certain way. Okay, so what we're going to do next is that we're going to learn how to make these limitations about the motion possibilities. And that's going to be with help of constraints. Let me take a look. There is a comment. Okay, so there's a question about, is it enough to be able to use this position, velocity, and acceleration? Or do you need to be able to derive something? And never ever asking you to derive anything. So if there's an equation, I'm going to give the equation to you. So I'm expecting you to understand the concept behind, physics behind. So I might ask a physical interpretation, but never asking you to derive anything. So that's for your information. Okay, but so mathematically, what it means. Mathematically means that if we have this vector of generalized coordinates that is defining configuration of all the bodies in multi-body system, then I'm going to introduce some links between these coordinates. And these links are the ones that are called constraint equations. So they are limiting the motion possibilities. And there could be a number of limitations. And each one of them, if they are independent with respect to each other, they are called constraint equations. Here I have an example which says that there is a NC number of constraints. NC number of constraints, number of generalized coordinates is n. This is, how much there is a possibilities to move without any constraints. Then the constraints are limiting the motion possibilities. Number of degrees of freedom, which we will discuss in details later, can be computed in a way that you can compute the number of generalized coordinates minus number of independent constraint equations. That's your number of degrees of freedom. Let me give you an example. No, I'm not going to give you an example because I will first want to take a look at these constraint equations to give you a better insight, like what is going on in these constraint equations. I think the easiest way to get started is by looking at an example. So I have here, oh my God, these slides I keep on moving the wrong place all the time. So here is back. Okay, I have here two bodies. Potato-shaped bodies again. The body called A, this guy here. Let me change the color to make this more clear to you. Green. And the body B. And these two bodies are connected together via a revolute joint. So it's like this kind of configuration. I have here beam-like body and beam-like body, and they're connected together here, which is a revolute joint. How is that you could describe the revolute joint mathematically? Okay, so that's a challenge for us. Okay, I think we can make it happen easily when we're using these kinematics we learned to use earlier. So we can describe this point here using body reference coordinate system. This body reference coordinate system like this. And we can redo the whole thing by using this body reference coordinate system. And once we have these two definitions, we're simply saying that these two equations have to be equal, meaning that this point have to be shared by body A and B. That's your revolute joint. Because it says that the bodies can do whatever they want. They can travel together like this. They can rotate together like this. They can do this. But they cannot anymore separate it from this point where the joint is located. So this is fixed. So mathematically, it can be expressed like shown here. Very simple. So let's just do the math. Let's make it happen. So how is that you can describe this point here using the kinematics that we are aware of? Okay. First, let's translate the origin of the body reference coordinate system using this vector R. All right. Then let's take the orientation of body reference coordinate system into account. Rotation matrix associated to first body. And then we can travel from the body reference coordinate system to place where the revolute joint is located at. Vector U bar. So not difficult at all. What about the next body? Well, next body, we could do exactly the same procedure. So we first translating where the origin of the body reference coordinate system is located at. RB. We are counting the orientation of body number or body B. Rotation matrix B. And then we're traveling where the body or this joint is located at, vector U bar. Nice. Okay, so then you have this expression. What you need to do is that you need to do the math. You need to be able to express this constraint in algebraic form. So you need to multiply this matrix by this vector You know how it goes, and if not, take a look at the Khan's Academy. And you do the same here. You have vector plus vector, you're multiplying the vectors, you're moving everything to the left-hand side of the equation, and this is your constraint, saying that, you know, these two vectors, the difference between these two vectors have to be 0 no matter what. That's your revolute joint. So it's very simple, very simple. And that's how we can make other types of constraints as well. How? That I'm not going to explain to you today, but it's going to be next week that I'm explaining that to you. Okay, so let me see. Here's something that we described already. Degrees of freedom, number of degrees of freedom. So number of generalized coordinates minus number of constraint equations. Let's test. Here is a pendulum. No, I need to change the color just a second. So here is a pendulum. Okay, so if this is a pendulum, the one body, how many generalized coordinates is needed to describe one body? That's 3. So it's Rx, Ry, and angle theta. Okay. Then you have revolute joint here in the pendulum that connects this beam-like body to ground. To describe that revolute joint, how many constraint equations you need? Well, we just learned here that to describe the revolute joint, you need 2 constraint equations. Okay, so it's going to be C1, C2. Number of degrees of freedom will be 3 minus 2, meaning that there's a 1 degrees of freedom system. So the pendulum is a 1 degrees of freedom system because the pendulum can move in a one way. So it's how many different ways your mechanism can move. Here is one way, because, you know, this is the only way. You know, the amount of rotation is something that I don't know, but it's just a one way. So the pendulum cannot move like this. Pendulum cannot move like that. So it's limited in that perspective. And then I'm blocking the view, so let me see what it says. Where n is a number of generalized coordinates, nc is a number of constraints. Right, just what I explained. Okay, let's move on. I see that I still have a little bit of time left. Not much, but a little bit of time. So let me look at the cons at the degrees of freedom. And oh my God, this is so annoying that these slides keep on jumping. So let me try to fix it here. No, that was too much fixing. Look at that. Okay, so why we need 2 constraint equations to describe a revolute joint. Let's take a look at the revolute joint in the case of that pendulum. By the way, awesome question. Awesome question. If somehow I need to find a way to give extra points for good comments or questions. Okay, so so let's take a look that there is a revolute joint located in the one end of this beam-like body. Let's think about that, you know, the body reference coordinate system is located here. All right. So what we can do is that we can describe this point, and let's say that the global coordinate system is located here, like this. Okay, so let's say that this is where this point or this beam-like body is located to constrained to ground. So we can express this location, is that's the way that we have R here. Then we're taking the rotation of the body reference coordinate system into account, which is a rotation matrix. And then with help of vector U bar, we go into this direction. So what we're going to say is that this vector here, this vector R, which I just expressed here, have to have a certain values all the time, constant values. How much are the constant values? These are the, you know, the values it must have. So this projection, which is a Rx, this one, and this projection, which is Ry. This is where your 2 constraint equations comes from. So this is simply where it is. So if you would say that, okay, the body actually can be, I mean, out of these two constraints, let me think. This is no longer valid, so it can change as however it wants. It means that the body can be within the slots like this. So the only thing that is limited is the limit of this point with respect to y coordinate axis. It can still translate to this direction, it can still rotate. So it depends like how many degrees of freedom you're plucking away or you eliminating from your system. And the revolute joint is eliminating two motions because it eliminates the motion in a global x and y direction and relative motion between the two bodies. They cannot separate it from this point anymore. That's what it is. Hopefully you're happy with my explanation. I can try to explain that in a little bit of different way next week too. But happy? Okay, because of the delay, I guess it takes a little while to get the answer. Okay. Meanwhile, let's take a look at the different scenarios. The different scenarios are related to number of degrees of freedom. Okay, thanks. Yeah, no worries. This will be something that we will explain so many times that you will be bored to death. Like, okay, when this ends. So no worries. But let's go back to these degrees of freedom and different scenarios related to this degrees of freedom. So let's take a look at the crankshaft. The crankshaft, let's first compute like how many degrees of freedom crankshaft have if there is no any special tricks. So let's see, we have how many moving bodies? We have 1, 2, 3 moving bodies. So how many generalized coordinates we need in that case? We need a total of 9 generalized coordinates. Then let's take a look how many constraints we have. We have here revolute joint, revolute joint, revolute joint. Each one of the revolute joint needs 2 constraint equations, so it's going to be 3 multiplied by 2, which is 6. And then there is one more joint here, which is a translational joint that needs 2 additional constraint equations, which is just given to you. This is going to give you 8. So there's a 1 degrees of freedom system. So the crankshaft mechanism can move in a one way only. You know that, it's using engines, so this is not a big surprise to you. So there's a 1 degrees of freedom system. Okay, so if there's a 1 degrees of freedom system and you introducing the motion to this 1 degrees of freedom system by moment or force, it means that it's dynamically driven. So in order to solve the response of this system, there's no other way than creating the equation of motion and solving the equation of motion in forward of time. But these things can be a little different. And things can be a little different because, what I can do is that I can eliminate these 1 degrees of freedom by introducing additional constraint. Additional constraint could be, information concerning how this piston can move back and forth. I could tell to this piston, okay, you cannot move freely left and right, but instead you have to follow the certain equation, which could be like sine time, meaning that this is a driven constraint. I'm moving or forcing this piston to move because of my driven constraint, but it's a constraint. So it's eliminating this 1 degrees of freedom such that the degrees of freedom is equal to 0. And this system is no longer a dynamic system, but it's kinematic system, meaning that its response can be fully solved by using kinematics, constraint equations, nothing else than the constraint equations. Then there's, of course, one more scenario, which is like there's too many constraints and number of degrees of freedom is negative, meaning that the system cannot move anymore. Yep, that's possible too, but that's a not too interesting configuration for us. Here are the different scenarios. So our constraint system is system that cannot move because, I'm introducing additional revolute joint here in a connection rod such that the connection rod is attached to ground. So this system cannot move. So it's stuck. Then I can introduce constraint. And the constraint could be the fact that this crankshaft have to follow the equation that is provided here. So this is driven constraint. So it's no longer free to move as it wants, but it have to follow this. Oh my God. Again, I touched the keyboard, so my mistake. So you see that what is a next in class quiz, which is the last one today. It was my watch. Okay, better now. So this is now constraint equation, because originally we have 1 degrees of freedom, one more constraint equation, so it's going to be 0 degrees of freedom. And I can solve the response by using constraint equations and vector constraints. That's the only information that I need, nothing else. How that happens? Well, no worries. I'm going to explain that to you partly next week and week that follows. So in next 2 weeks. Or then we can have a dynamically driven system, which we are driving this system by using forces or moments. That's what it is. Let's just try to make this clear one more time, because this is very, very fundamental. If you have a box sliding in this ground, so the box is connected to ground via translational joint. So only possible motion of the box is back and forth in x coordinate axis, along the x coordinate axis. Okay, so what you can do is that you can introduce the force that is pushing the box to move right hand side direction. All right, so what you need to do to solve that response? Well, you need this force, and you need to create the equation of motion to solve the response. No other way. But what you could also do is that you can introduce the constraint. And the constraint is not the force, but the constraint. Constraint which says, okay, this point here, which belongs to the body, have to follow the path that is provided as a sine times something. So it forces this box to follow this pre-described motion. Pre-described motion. And then it means that the number of degrees of freedom is 0. So we learned something important here too. So the constraints are always more powerful than forces. Constraints never break. Forces are much weaker than the constraints. So if there is a like 4-bar, well, crankshaft mechanism like this, no matter how forces you press in this direction, the constraints never break. Even if we take like huge power, like this one, still I cannot break this system, because constraints are more powerful than any force in this earth. So that's what it is. Let me see. Yeah, I promised last in class quiz, and then I'm done for today. And it's this one. Number of degrees of freedom in dynamically driven system. So the system that you can solve by using, number of degrees of freedom in kinematically driven system. So the system that you can solve the response by using kinematic analysis. What is the number of degrees of freedom in that case? Less than a 0, equal than the 0, more than a 0, more than 100. Let me hear you. So this is the last in-class quiz of the day. You're good to go. And here it is. Oh, we could, record the speed to get the answers. And then let me find out the link there for the question and answer session in Teams. And the game is on. Oh yeah, now here's my man, 200%. That's clear can-do attitude. I need to give the extra point because of that. Yeah, 100% would be nice, but I don't believe that by myself. I would be very surprised if we got 100%. I would be shocked if we're going to get 100%, which I don't think going to happen. That never happens. Never happened in my career. So I think maybe it was once. But then I was asking something ridiculously simple, not difficult like this. 66 students, and again, this link that I promised to you, that will be in a chat window momentarily. let me just open my calendar. It's a bit slow calendar today. Okay, where that I can find it? Was it last week? Here, yeah, this is where can I find it. Join the team. Oh my God, I don't think I can copy that for you. Or can I? Copy hyperlink. Okay, let's try. There's a chat window, paste. All right, try this. Hmm. I don't know why it's not able to give me that. I cannot give that to you. I'm sorry about that. Don't know. I don't know why. But you need to just take a look at your message that I emailed you through the modal database. So that should give you to access to Teams question and answer session. But now this one. So is it going to be 100% or not? No, it's not going to be 100%. But how much? 90. Record number today. Record number today. So we're getting better. You know, maybe we should not close to this. Maybe we should keep on going for next 2 hours, and finally we will hit the 100%. Good job. Good job. Hey guys, thank you very much. And once again, apologize. I would like to apologize about the technical difficulties, which is surprising because I'm here in a university in my home. I mean, here, not in my home, but in my office. And everything here should be as strong as possible, but it's obviously not. Okay, so I'm going to close the streaming and see you soon in a team session.